Alright, let's take a look at the periodic trends of elements, right? And these periodic trends are just certain chemical trends that you would expect by using the periodic table of each particular element. These periodic trends are really useful in determining chemical reactivity, which we'll be discussing soon. So some of the periodic trends that we will be looking at are going to be the size of an atom, right? And remember that atoms include or encompass charged atoms called ions and neutral atoms called elements. Okay, so for elements we're going to be using the atomic radius for the most part. Okay, so the atomic radius, I'm going to abbreviate the atomic radius as AR. And for charged atoms, for ions, we're going to be looking at the ionic radius. Okay, so for both of these cases, they're going to describe the size of the atom itself, right? We're also going to be looking at the ionization energy. So I'm going to abbreviate this as IE. And we're also going to be looking at electronegativity. I'm going to call this EA. Now, particularly the ionization energy is the energy needed to remove an electron. The electronegativity, electronegativity. Let's rewrite that again. So the electronegativity here is basically the attraction of a positive nucleus to a set of electrons. So it's how strongly the nucleus will attract electrons, or how strongly an atom or will hold electrons. It's hold its electrons, right? And we'll also look at another concept called electron affinity. Okay, so we're going to call this, for electronegativity, I should have said EN. Sorry about that. EN for electronegativity, and EA for electron affinity. Electron affinity is the energy released when an electron is added into a system, right? And the more energy that is released, the more spontaneous the process is, so the less energy it's required to add the electron in, right? So we're going to be looking at these 5 major trends, right? But before we actually look at these 5 major trends, I'm going to show you how the periodic table can demonstrate if you're comparing 2 elements in these trends. But before we actually look at this, we need to kind of identify a few things. Specifically, we need to understand relative energies of electrons and how that is dependent on their separation distance as well as the force of attraction by the nucleus. Now, we know that Z is the nuclear charge, so I'm just going to identify a few things that we're going to be discussing when we describe each of these 5 major trends. Okay, so we're going to be looking at Z, which is the nuclear charge, and the nuclear charge is the number of protons found in the nucleus. So you can see that it's given the same letter as the atomic number, because it really represents the charge is basically plus Z, right? So it is technically the atomic number, right? So Z is the atomic number. And this is basically the charge that the nucleus will have at all times, right? Now, we're going to use R for separation distance to discuss electron position from the nucleus, separation distance of electrons from the nucleus. Right? And we know that electrons are located in different locations, specifically different orbitals, different subshells, different shells, right? So if I was going to look at an element, and let's just use Bohr's model to kind of describe this really quickly. If I was looking at an element like oxygen, right, which is going to be described as having 8 electrons, right? In the first energy level, so it's 8 protons, 8 neutrons, because this guy has an atomic mass of 16, right? So it has 8 protons, 8 electrons, 8 neutrons. I'm looking at elemental oxygen, right? We can notice that the nuclear charge here is 8, so the charge here is going to be plus 8. Okay, so the nuclear charge is +8. We can look at each proton as having a +1 charge, right? And this is always going to create a +8 charge. Now, the electrons are going to be found around the nucleus in these shells, right? And each shell has what we discussed earlier, given subshells and orbitals particularly, but it's not too important right now. We're going to have 2 electrons here, and we're going to have 8 electrons here. I'm just going to group them into their respective orbitals. Okay, I'm just using Bohr's model just to make it simpler, right? And a few things we want to kind of look at here is that our valence shell, oh, sorry, I should have had 6 electrons, not 8 electrons. So let's just get rid of the 2 here. So 6 electrons on the valence, right? And one thing we need to look at here, this is the first energy level, right? This is the second energy level. And what you need to take a look at is basically one of these energy levels is going to be your valence shell. The other energy level will be your non-valence shell. Now, the non-valence shells are called core electron shells. This is a core electron shell. It's a completely filled electron shell, and it's not involved in bonding. N is equal to 2 represents your valence electron shell. Now, what the core electron shell does is it actually causes some of this attractive force, right, the nucleus creates. So let's say that this is the attractive force that the nucleus creates, 2 electrons. What the core electron shells will do is they actually disrupt, right? They disrupt the force, right? So they actually weaken it, right? So if we're looking at, well, this keeps happening. If we're looking at the attractive force that these further electrons feel, the core electron shells will disrupt that nuclear charge, and as a result, the nuclear charge will get distorted depending on the location of the electrons, right? So although we said that the nuclear charge is the intrinsic charge of the nucleus, the effect of that nuclear charge on electrons will be dependent on the distance as well as the core electron shells. Now, the core electron shells will create a force that repels electrons, right? If you have filled valence shells, if you have filled electron shells, you have repulsion of electrons, and this repulsion is called shielding. Okay, so shielding is basically the repulsion of core electrons in core electron shells. Okay, so in core electron shells, where we have filled shells, these electrons will repel each other, and shielding will actually disrupt. Shielding actually will disrupt the nuclear charge. Specifically, the nuclear charge's effect on further electrons. Okay, so the shielding will disrupt the nuclear charge's effect on further electrons, right? So this is an important concept to understand. So because the nuclear charge of the nucleus is going to be constant, but the effect of that nuclear charge will be dependent on shielding as well as the distance of electrons, we need to look at a different term. Okay, so we talked about shielding. Shielding is basically the repulsion force of electrons located in core electron shells, right? So we gave the example of if we looked at oxygen, right, then oxygen would have 8 protons, 8 neutrons, right, and then these would be the shells here, right? And if I was going to put the electrons located here, there's going to be 2 electrons here, and then there's going to be 6 electrons here. I'm just using Bohr's model, so it's really simplistic. We can notice here that the nuclear charge is +8, right? Nuclear charge is the number of protons, right? And each proton has a +1 charge. That's what we can simplify it to. So there's 2 electrons in the first shell, and there's 6 electrons in the second shell, right? And we can understand that the nuclear charge is going to be constant. However, the effect of the nuclear charge is going to be dependent on the separation distance of the electron from the nucleus and the shielding effect. Okay, so we can understand that as the separation distance increases, right, the effect of the nuclear charge, which I'm going to call Z effect, the effect of the nuclear charge is going to decrease. Okay, because we can understand that the further away electrons are from the nucleus, the less force of attraction it'll feel, right? Because we know that electrostatic forces between charges are dependent on distance. As the separation distance to the nucleus decreases, the effect of the nuclear charge will increase. Okay, so we're going to call Z effect the effect of the nuclear charge. We can even call it the effective nuclear charge. Right, so although the nuclear charge is constant, the effective nuclear charge is dependent on separation distance and the shielding effect. Now, if we're looking at the shielding effect is going to cause some of the nuclear charge to be distorted, right? Shielding reduces the nuclear charge's effect. Right, so as a result, as shielding increases, I'm going to use S for shielding. As S increases, the effective nuclear charge decreases. As shielding decreases, the effective nuclear charge increases. Technically, you can think about the effective nuclear charge as the nuclear charge minus shielding. Okay, so in shielding, we're going to look at, to calculate shielding, we're going to look at the number of electrons in core electron shells. Okay, so for shielding, it's the number of electrons in core electron shells. In the case of oxygen, we had 2 electrons in the core electron shell, so S is equal to 2, right? And Z is the nuclear charge, and Z effect is the effective nuclear charge. If you're looking at the charge in the second energy level, the effective nuclear charge that's imposed on the second energy level, the effective nuclear charge is equal to 8, the nuclear charge, right, minus, there's 2 core electrons that's present, and you get positive 6. So now you can see that it diminishes, right, over time. So the more electrons that you have in a shell, and the more core electrons you have, the more the charge actually diminishes. So this is actually a really useful way of looking at the effective nuclear charge. This is an oversimplification of the entire process, but I think it's effective in looking at that. So it's a good way to kind of look at how strong a force of attraction you have between the nucleus and the electron. The reason we look at the force of attraction, really the effective nuclear charge is the force of attraction. The reason we look at the force of attraction is because of the fact that it tells us something about the kinetic energy of the electrons, right? So as the separation distance increases, we can understand that the effective nuclear charge will decrease. If the effective nuclear charge decreases, this tells us that the force of attraction that holds the electron in the atom also decreases. So if the force of attraction decreases, then the kinetic energy of that electron, right, is going to increase. Right, and if the kinetic energy of the electron increases, the reactivity of that electron, so its ability to collide with other electrons and be exchanged, will also increase, and vice versa, right? And we can also consider shielding. If we have more core electron shells, right? If we have more core electron shells, we have more shielding, and as a result, more shielding means we've decreased the effective nuclear charge, and as a result, if we decrease the effective nuclear charge, the force of attraction decreases, and as a result the kinetic energy increases because now there is less force of attraction, and then there's more reactivity. So you guys can think about the converse case, right, of this, right? But it's really important to understand the effect of separation distance and shielding on this effective nuclear charge. Really, at the end of the day, we need to assess the kinetic energy of electrons. So that's how we can understand how chemical reactions will occur. Alright, let's take a look at atomic radius. So atomic radius represents the distance of the nucleus to the valence-most shell. Okay, so this is the formal definition of atomic radius. It's really a way for us to classify the size of an atom, right? So if it's the distance of a nucleus to the outermost shell, this is like a certain atomic structure according to Bohr-Rutherford, then this would be the atomic radius. So let's say this is the valence shell, n is equal to 2, and this here is the atomic radius, right? You got to think about this in a three-dimensional perspective. That's the idea. Now we're going to really use atomic radius for neutral atoms. For charged atoms, we're going to be using ionic radius, which I'll talk about afterwards. But the atomic radius is going to have two general trends. The increasing trends here, the increasing trends for atomic radius, the atomic radius will increase to the left of the period and down a group. Okay. Now the decreasing trends for atomic radius, so decreasing trends I'm going to do in blue, right? The atomic radius decreases to the right of a period and up a group. I'm going to explain why this is the case, right? I'm going to explain the type of trend regarding atomic radius for each of them. So if I'm looking at the atomic radius here, if you're going from the right right to left on a period, so if you're going towards the left on a period, the atomic radius will essentially increase. And what that means here is that, let's say increasing trend. And what this tells us is that atoms to the left of the period relative to another atom are going to have a larger atomic radius, which means that they are larger in size. The reason for that is as you go to the left of the atomic radius, you're going to be found in the same period, right? So for instance, if I'm looking at period 2, so lithium, beryllium, boron, carbon, whatever, right? As I go from oxygen to nitrogen, nitrogen to carbon, carbon to boron, if I'm looking at neutral atoms or elements, the size of the atoms get bigger. So boron is bigger than carbon, carbon is bigger than nitrogen, etc., right? So the size of the atoms will get bigger, and the reason for this is because what's going to happen is as you go to the left of the periodic table, left of a period, the nuclear charge decreases. So as the nuclear charge, and you can tell that the nuclear charge decreases because if I go from fluorine to oxygen, fluorine has 9 protons, oxygen has 8 protons, right? So as you go to the left, the number of protons decreases. As the number of protons decreases, the effective nuclear charge should also decrease. Okay, so the effective nuclear charge, or the force of attraction that each electron will feel, will tend to decrease. If the effective nuclear charge decreases, this implies that the force of attraction from the nucleus to a particular electron decreases, right? Specifically, we're going to be looking at the valence electrons, right? Because we can understand that the size of an atom is arbitrarily based on the electrons and where you find them, right? If the size of the atom is large, that means that the electrons are spaced a lot further away from the nucleus and vice versa. So because the force of attraction decreases as you go to the left, this causes the kinetic energy of the electron to increase. So now if the kinetic energy of electrons increases, the electrons will move outwards, right? And basically, so electrons would move outwards here, right? So if electrons move outwards, then the size of the atom tends to increase. So that's why the atomic radius increases to the left of a period, because of the fact that the atomic number, or the nuclear charge decreases. Nuclear charge decreases to the left of a period. And you can think about this in the case of its opposite trend, right? That the atomic radius should decrease if you go to the right of the period, right? And this is a decreasing trend. It's a decreasing trend because of the fact that as you go to the right of the period, the atomic number increases, which means that the nuclear charge increases, which causes the effective nuclear charge to increase. right? And because the effective nuclear charge increases, the force of attraction will tend to increase, and as a result, the kinetic energy of the electrons decrease. So in that sense, if the kinetic energy of the electrons decrease, now what's going to happen is instead of being out here, they're going to be being pulled in now, right? So they're actually going to be closer to the nucleus, right? So they're actually going to be closer to the nucleus. So the size of the atom will shrink. Okay, so the size of the atom is just associated with the location of electrons. And the location of electrons is associated with their kinetic energy. If electrons have low kinetic energy, that means there is a larger force of attraction, and vice versa. Let's take a look at the second trend that we have here. And this time, we said that atomic radius increases down a group, right? Let's explain why it increases down a group. So as you go down this way, down a group, the atomic radius will increase. That means that calcium will have larger size than magnesium, potassium is larger size than sodium, sulfur is larger than oxygen, and so forth, right? Explanation for that, as you go down a group, the most prominent thing that increases is the shell number. So the shell number n increases. The shell number increases, the number of core electron shells increases. Because the number of core electron shells increases, the shielding effect will increase. Because shielding increases, the effective nuclear charge will decrease, right? Because we said earlier that the effective nuclear charge is the nuclear charge minus shielding. Well, as this increases, then this will decrease. Okay, and as the effective nuclear charge decreases, then the force of attraction decreases between the electron and the nucleus. Specifically, we're looking at the valence electrons. So I think the valence electrons are probably the most important electrons to consider when we're looking at atomic radius. And as the force of attraction decreases, the kinetic energy increases, and now electrons can move further away, right? And the size of the atom gets bigger, and vice versa, right? So this is important. It's really important to understand the shielding effect here. That the shielding effect occurs when you go down a group, right? And this is the most prominent effect that causes the atom to get bigger and bigger. Okay, so let's take a look at some examples. But what you need to kind of understand is these two trends, right, that I've highlighted out here. Make sure you understand these two trends for atomic radius. The increasing trend in red, atomic radius increases to the left of a period down a group. The decreasing trend in blue, atomic radius increases up a period, up a group and to the right of a period. Okay, let's take a look at ionic radius. So this is kind of like the atomic radius analogous to ions. And we need to distinguish between two types of ions. Positive ions known as cations, and negative ions called anions. Okay, so anions are negative, cations are positive. In general, cations will be smaller than anions, right? So it's going to be a little difficult for us to compare cations to anions. We tend to compare each of the ions relative to themselves. Like I would compare two cations together, I would compare two anions together. It's kind of hard to crosstalk between cations and anions, right? When you're comparing just cations together, you can still use the same trends as atomic radius. So we know that the atomic radius tends to increase to the left of a period and down a group, right? For the same type of ion, right, and this is going to be an increasing trend. For the same type of ion, the ionic radius will increase to the left of a period and down a group, right? So this only works when you're comparing two cations together or two anions together. You don't tend to do the two crosstalks, right? Vice versa, a decreasing trend we stated earlier for atomic radius decreased to the right and decreased up a group, and for the same type of ions we do the same thing. So it's really the same idea. The ionic radius also decreases to the right and up a group if you're only comparing the same type of ion. Now, if you're comparing cations to anions, anions are always going to be larger than cations, right? And vice versa. The reason anions are always larger than cations is because within the same shell, if I compare oxide, right? So oxygen is 8 protons, 8 electrons, right? And there's going to be 6 valence electrons, right? There's 6 valence electrons. The oxide anion, -2, is going to be a stable octet. So it's going to have to gain 2 electrons. So let's say that it gains these 2 electrons. Okay, let's make these 2 the electrons that it gains. Okay, so these are the 2 electrons that the oxide anion gains, right? In this sense, you can notice here that now in the core this essentially creates a core electron shell, right? So because of that, you actually have more electron repulsion. So because you have more electron repulsion, what's going to happen here is that it reduces the effective nuclear charge, and the electron repulsion causes the valence electrons to repel outwards. Because the electrons repel outwards, initially your shell would have been like this for your second shell, but now because of repulsion, right, it's being shifted and it expands, right? It's being pushed outwards, right? So the size of an anion is going to be larger than its element because it's gaining electrons, right? So the ionic radius of an anion will always be greater than the atomic radius of its element. Okay, so let's just say anion. Conversely, if you're looking at a cation, let's take a look at magnesium, for instance. Okay, so magnesium has an atomic number of 12, it has 2 valence, right? It has 12 protons, 12 electrons. And let's take a look at magnesium plus 2. Well, this is basically 12 protons, 10 electrons, right? You can notice that the nuclear charge here, the effective nuclear charge, is going to be the nuclear charge minus shielding, right? And we're going to do the same thing here. Now for magnesium itself, in the first shell you should have 2, the second shell you should have 8, the third shell you should have 2, right? So this is n is equal to 1, n is equal to 2, n is equal to 3. Okay, so now what you have here is you have 10 electrons for shielding, right? So, but because you have the 2 electrons here, what's going to happen is there's going to basically be more electron repulsion here versus in this case where you're going to have 2 electrons in the first shell, 8 electrons in the second shell, right? So the plus 2 charge now, because if you looked at an electron in this shell, the plus 2 charge now is going to tell us that the charge of the nucleus is greater than the charge of the nucleus is greater than the number of electrons, right? So because you have a plus 2 charge that's in excess, then what's going to happen is the electrons get attracted to the nucleus stronger. Okay? So because the electrons get attracted to the nucleus stronger, now the valence shells, they shrink. Okay? So they actually shrink inwards, not to this extent, but they shrink inwards, right? So the size of the ion gets smaller. So that's why cations tend to be smaller than the respective atomic radius of their element, right? So the ionic radius of a cation tends to be smaller than the atomic radius of its own respective element, and the ionic radius of an anion will always be greater than the ionic radius of a cation. So ionic radius of anion is always greater than ionic radius of cation. Okay, so for the most part, we're only going to be comparing this same type of ions, cations to cations, anions to anions. Okay, let's take a look at electronegativity. It's called En for short. Let's abbreviate it that way. And electronegativity is basically the ability of a nucleus to attract electrons. Specifically, it can also describe the ability of an atom to hold its electrons. Okay? So largely electronegativity, the stronger that an atom will hold its electrons, the stronger that it will attract external electrons, and vice versa. Right? As a result, you can understand that nonmetals tend to have a higher electronegativity, metals tend to have a lower electronegativity. The reason for that, so metals tend to have low electronegativity, so that's as a result they tend to lose electrons. Nonmetals, they tend to have a higher electronegativity. Right, so they have a higher electronegativity, so as a result they tend to gain electrons. The electronegativity trend, the increasing trend, I'm going to do that in red, the increasing trend of electronegativity increases to the right of a period and up a group. Okay, so this is your increasing trend. Increasing trend. The decreasing trend of electronegativity decreases to the left of a period and down a group. Okay, so this is your decreasing trend. And the idea here is how do we explain this, right? So let's take a look at explaining the increasing trend. Okay, so I'm gonna look at to the right of a period, and let's take a look at the increasing trend up a group. Right, and whatever we look at for the increasing trend, you can think about for the opposite scenario for the decreasing trend. So why does electronegativity increase to the right of a period? Well, if you go to the right of a period, what's going to happen is, if you compare like nitrogen and carbon or oxygen to nitrogen, when you're in the same valence shell, you can understand that the nuclear charge increases, right? So if the nuclear charge goes up, okay, if the nuclear charge goes up, then the effective nuclear charge also increases, right? So the effective nuclear charge increases as the nuclear charge goes up, right? And the effective nuclear charge is the effect of the nuclear charge on a particular electron. As the effective nuclear charge increases, then the force of attraction to electrons increases. Then force of attraction, electronegativity is really the force of attraction of electrons. So you can think of this another way. So as a result, the electronegativity increases, right? Because now there is a stronger force of attraction. Okay, so that's how you can attract external electrons. You can hold valence electrons stronger. So that's the idea. And that's why nonmetals tend to gain electrons, because they're actually located on the right side of the periodic table. So this is like a dividing line here. So I think they kind of drew this out, but you can see that the metalloids are in this grayish tealish area. I'm just going to kind of separate this with the nonmetals. So I'm going to separate the nonmetals, metalloids from metals here. That's why nonmetals are found on the right side of the periodic table, and they tend to have a larger electronegativity, right? So that explains one of their characteristics. Now, if we're looking at going up a group, right, so electronegativity up a group, how we can explain this, why does it increase? Well, if you go up a group, like if I go this way, you go up a group, the shell number decreases. The shell number decreases, the number of core electron shells decreases, so the number of core electrons decreases. If the number of core electrons decreases, the shielding effect decreases. If the shielding decreases, right, so if we have a decrease in the shielding effect, then we basically have a larger effective nuclear charge, right? Because the effective nuclear charge gets diminished by the shielding effect using this equation that we showed earlier, right? So if this decreases, then this increases. As the effective nuclear charge increases, the force of attraction from the nucleus to the electron increases, and as a result, the electronegativity increases. Okay, so what I want you to kind of do here is I want you to take the opposite scenario for the period and the group, the opposite trend, and I want you to kind of explain that, but think about how all of these things will change in that result. Okay, so moving along on our discussion about periodic trends, what we're going to be looking at now is called ionization energy. So ionization energy is basically the energy required. I'm just going to abbreviate it as IE. It's the energy required to remove an electron from the valence shell. Okay, so we're just removing electrons from the valence shell. We can understand that electrons are found within an atom, and there is a force of attraction that holds the electron in the atom, so you have to employ energy into removing that electron. Now, different atoms or different elements will have different number of valence electrons, right? Like for instance, if we had potassium, which has 1 valence electron, versus magnesium, which has 2 valence electrons, versus aluminum, which has 3 valence electrons. Okay, these guys have different numbers of valence electrons. I'm using the Lewis dot symbol to show valence electrons. As a result, you're going to have multiple ionization energies in certain cases, right? Like for instance, if we're looking at potassium, if we remove the first valence electron, right? We know potassium has 19 protons, 19 electrons. If we're looking at elemental potassium, once I remove that valence electron, now potassium here, right, becomes a +1 charge, so it becomes a potassium cation. So now it has 19 protons and 18 electrons, right? If we take a look at magnesium, right, this guy has 12 protons, 12 electrons, but there's 2 valence electrons. So if I remove one of the valence electrons, then we're going to get Mg +1. Right now it has 12 protons and 11 electrons, right? And this ionization energy is called the first ionization energy. Okay, so there's different number of ionization energies if you have multiple valence electrons, right? So this one here would also be the first ionization energy, but potassium only has 1 valence electron, right? After you removed one of magnesium's electrons, then there is another electron that you still need to remove, and this is what we call the second ionization energy, right? So IE1 is the first ionization energy, and IE2 is what we call our second ionization energy. And the fact here is that the second ionization energy is significantly greater than the first ionization energy. Okay, so this is the second ionization energy that requires to get to Mg +2, right? Likewise, for aluminum, this guy has 13 protons and 13 electrons. If I wanted to create an aluminum cation, I'm going to use a different color for this, right? If I wanted to create an aluminum cation, I'm going to first remove 1 electron. This is the first ionization energy, or the energy needed to remove that first electron, and I get aluminum +1, because now it has 13 protons and 12 electrons. But then I need to remove the second electron, so this is your second ionization energy, right? And then you get aluminum +2, so this guy has 13 protons and 11 electrons, and then the last ionization energy is my third ionization energy, and you're going to get aluminum +3, and now it has 13 protons and 10 electrons. And similar to magnesium, our third ionization energy is significantly greater than our second ionization energy, which is significantly greater than our first ionization energy. And we want to ask ourselves, okay, why is the second ionization energy so much bigger than the first ionization energy? Why is the third ionization energy so much bigger than the second ionization energy? Well, if we take a look at magnesium +1 with 1 valence electron, right, versus magnesium, elemental magnesium, right, we can understand that this guy here is going to have a really high effective nuclear charge. The reason it has a really high effective nuclear charge is because of the fact that now there's more protons than electrons, right? Now, because you have 12 protons here and 11 electrons, and now there's a much stronger dominant force, right, attracting the electrons. And there's also less shielding of electrons, right? Because you have less shielding, there's a large effective nuclear charge, which increases the force of attraction, which reduces the kinetic energy, and as a result, this also reduces the separation distance, right? So the ionic radius of magnesium +1 is significantly smaller than the the atomic radius. Just gonna clear that up a little bit. Significantly smaller than the atomic radius of magnesium. Okay, so the cation form of its ion is going to be a lot smaller than the atomic radius, and as a result, there is going to be much stronger ionization energy, right? If you have a really large force of attraction, if you guys take a look at this portion here, if you have a really large force of attraction, well, sorry guys, I don't know how that happened. So if you have a really large force of attraction located here, if you have a really large force of attraction, then it's going to take a lot of energy. It takes a lot of energy to remove electrons. So that's why the second ionization energies, the third ionization energies, they get significantly stronger because of the fact that, right, the size of the atom is getting much smaller because of the effect of nuclear charge. So this is the really important idea, right? The force of attraction is getting really strong. Okay, and you can apply this notion also to the third ionization energy for aluminum, right? It's the same notion that the ionic radius of these cations will get smaller and smaller, right? And in the opposite scenario for anions, they'll get bigger and bigger. So you can imagine that the ionization energy gets smaller and smaller. Okay, so that's the idea. And in this case, we want to kind of understand the trend of ionization energy. So if you're looking at ionization energy increases to the right of a period and up a group, and ionization energy decreases down a group and to the left of a period, right? So if we wanted to quickly just kind of explain this, I'm just going to make some space here just to kind of explain this notion. Right? If we're looking at why does the ionization energy decrease to the left of a period, well, we can understand that the nuclear charge decreases, right, because the number of protons decreases. As a result, the effective nuclear charge decreases, and as a result, the force of attraction that holds the electrons together decreases. So if there's a weaker pull that holds the electrons, then we can remove it a lot easier, right? So as a result, if there's a weaker pull that holds the electron, then the ionization energy should decrease. So you can imagine that there is a direct relationship between the force of attraction and the ionization energy. So it's going to be a positive correlation, right? We're looking at why does the ionization energy increase if we go up a group. Well, if we go up a group, what's going to happen here is the shell number decreases, and as a result there is less core electron shells, right? So the core electron shells will decrease, and there's less core electron shells, then what's going to happen here is that the shielding effect also decreases. So if the shielding effect decreases, and we know that shielding is very prominent, it's very significant, if the shielding effect decreases, then the effective nuclear charge will tend to increase. Now if the effective nuclear charge increases, we know that the force of attraction increases, and if the force of attraction increases, then there's going to be more energy required to remove electrons from the valence shell, so the ionization energy will tend to increase. So once again, it's a direct relationship between the force of attraction, the effective nuclear charge. You can kind of combine all of these three, right? So this also is included. Right? It's a direct relationship between these three variables, right? So it's really important to understand this, right? And we'll take a look at some relationships by doing some questions about ionization energy. Okay, let's take a look at the electron affinity. So the electron affinity is the energy released when an electron is added to a valence shell. And how we can look at the electron affinity is we can look at the electron affinity as the kinetic energy that an electron will have subtracted from the bare energy, right? Well, the bare energy is subtracted from the kinetic energy of the electron. Okay, I'm going to explain what each of these notions mean, right? The kinetic energy of an electron is just the amount of energy found in an electron in free space, right? So energy found and an electron in free space. Let's say that this is basically constant. Okay, so this value here is constant, right? Barrier energy, I'm going to call this barrier energy. This is the energy that resists, right? So this is the energy you need to bypass, right? This is the resistance or barrier of entry to add an electron in to an atom. Okay, so it's the energy that resists the addition of an electron into an atom, right? And you have to bypass this barrier energy in order to add an electron. And it's very important to understand here that if this is constant, our electron affinity will be dependent specifically on the barrier energy. Now, if I decrease the barrier energy, look what happens to the electron affinity, right? If this is constant, if I decrease barrier energy, then this value is going to get smaller and smaller, and the kinetic energy is going to subtract this smaller value and make a larger electron affinity. So this is, if you decrease the barrier energy, the electron affinity is higher. Vice versa, if I increase the barrier energy, so that means that there's more resistance to entry of an electron, right? Let's just do that out here. Okay, so there's more resistance to entry of an electron. If I increase the barrier energy, well, now the constant, the kinetic energy of the electron is going to be subtracted by a larger number and cause the electron affinity to be smaller, right? So this is going to mean a smaller electron affinity. Right, so you can understand that the barrier energy and electron affinity is inversely proportional. Okay, and what this means is that if there is more resistance, right, the larger the barrier energy, right, the less energy that is released, and vice versa. Okay, so this tells us that it's easier to add electrons into a system if more electron affinity is produced, right? So if more energy is being released, right? So spontaneous processes, right, or spontaneous addition of electrons will occur when the electron affinity is really high. So it's easy to add an electron in to an atom if the electron affinity of that atom or the ion or element is really high, right? So that's the idea, and vice versa. Okay, so it's really important to understand this, and there's a negative correlation between barrier energy and electron affinity, but we've got to ask ourselves, okay, what is affecting barrier energy, right? Barrier energy is the resistance of adding an electron in. Well, what affects the resistance, right? What makes it, what reduces the resistance of adding an electron in? Well, we can understand that if you have a stronger force of attraction by the nucleus to an external electron that you want to add in, then that basically means that the barrier energy should decrease. Okay, so if the force of attraction of the nucleus to external electrons is higher, then the barrier energy should decrease, and vice versa. If the force of attraction is lower, then the barrier energy should increase, right? There's more resistance in adding an electron in if there isn't that attractive pull that will basically cause electrons to come into an atom, right? We can understand that force of attraction can be dependent on a few things, right? Like the effective nuclear charge is directly proportional to the force of attraction. We stated that the force of attraction and barrier energy, based on this relationship, is inversely proportional, right? But the effective nuclear charge and the force of attraction are directly proportional. We also understand that the force of attraction is inversely proportional to the separation distance. So the separation distance is inversely proportional to the force of attraction, right? So this is also important to understand as well. And we can link these two together, right? So the separation distance is also inversely proportional to the effective nuclear charge, right? So collectively, if we increase the separation distance, we decrease the effective nuclear charge, therefore we decrease the force of attraction, and as a result we increase the barrier energy, right? Because there isn't that attraction force that's guiding electrons in, so there's more resistance to entry, and then this increases the electron affinity, right? So this is really important to understand, and everything can kind of just be summarized by this equation, right? So this equation at the end of the day will really kind of help you guys to understand this. So it's good to understand this relationship of barrier energy and electron affinity, and collectively we can come up with the periodic trend here that electron affinity increases to the right of a period and up a group, and electron affinity decreases to the left of a period and down a group. Okay, and once again we're just going to explain this trend further, so I'm just going to make some space here. All right, so let's collectively look at this trend. All right, and let's take a look at the increasing trend of electron affinity. Okay, why does electron affinity increase to the right of a period? Well, we can understand that the shell number, right? Sorry, not the shell number. The proton number or the nuclear charge increases, and as a result, because the nuclear charge increases, the effective nuclear charge will tend to increase, and as a result, the force of attraction increases. The force of attraction increases, then there is a larger pull and less resistance to add an electron in. So the barrier energy should decrease. If the barrier energy decreases, according to this equation, the electron affinity, there's more energy that's released when an electron is added, because less of it is required to add that electron in, right? So you're just subtracting from the kinetic energy of the electron. Let's take a look at a decreasing trend. So why does electron affinity decrease going down a group? Well, going down a group, the shell number increases. The shell number increases, there's an increase in number of core electron shells. There's an increase in the number of core electron shells. Then what's going to happen here is we're going to have a larger impact of the shielding effect. Because we have a larger impact of the shielding effect, what's going to happen is the shielding effect will cause a dilution of the effective nuclear charge, right? Because we understand that the effective nuclear charge is nuclear charge minus shielding. If this increases, then this is going to decrease. So in this case, the effective nuclear charge decreases. As a result, the force of attraction decreases. Now there's less of an attractive pull to add an electron in, so there's more resistance, right? So because there's more resistance, the barrier energy to add an electron in is a bit higher, and because the barrier energy to add an electron is higher, then the electron affinity, the energy release is going to be lower. So if something releases low energy, then it's not as receptive when an electron is added, and it'll take a lot more energy to do so. Okay, so that's the idea behind that. Okay, and we'll look at some questions and divulging these trends. Okay, so we looked at a few periodic trends, right? And I'm just going to recall that some of the periodic trends that we looked at was atomic radius, and we said atomic radius increased to the left of a period down a group. We also looked at ionization energy, which increased to the right of a period and up a group. We looked at electronegativity, which also increased to the right of a period and up a group, and electron affinity, which increased also to the right of a period and up a group. Right? Particularly these three things, right? These three trends here, they have really the same type of trend. They're positively correlated. They influence each other, right? And they are also inversely related to the atomic radius. Okay, so they're also inversely related to the atomic radius. So this is what we kind of talked about. However, there are going to be some exceptions here regarding, especially going to the right of a period, right? And the reason one of these exceptions exists is because even if you're in the same shell level, the valence shell, you can still change the separation distance from the nucleus because you can move to a different subshell. So recall that we looked at our periodic table. If I take this helium and I bring it here and I put helium out here, so this is helium now, right? Collectively, we said earlier that all of the species here they form the s block. Okay, so this is all of this is the s block, and the s block identifies the s subshell, right? All the species here, this forms the d subshell, and collectively are called the d block. Okay, so that's all of that notion there. So hopefully you guys can see that, right? So just kind of highlight that, right? All of this is the d subshell, right? This is a great way to kind of look at electron configuration. I would recommend reviewing electron configuration before you get back to this. So it's a good video to kind of go over before this lesson. But this portion here we said was the p block. Okay, and this represents the p subshell. And the one below here, we'll call this the f block. And this represents, this represents the f subshell. Okay, so the f block, this represents the f subshell, and we can use this to figure out the electron configuration, right? Now, there's basically going to be levels. Levels exist in given valence shells, and the valence shells are indicated by the period, number. And we showed that out here, right? This is period number 1, 2, 3, and this just tells you which shell the valence shell is, right? There's levels that exist in each valence shell, and these are called the subshell levels. Okay, like for instance, if I compare beryllium versus boron, right? The electron configuration of beryllium, which has 4 electrons, is basically 1s2, 2s2, right? We're only looking at the valence shell, so I'm just going to use the condensed structure to represent the core electron shell. So let's use helium here. Okay, so the valence shell here is 2s2. For boron, however, we have helium. I'm just looking at the valence shell. You have 2s2, 2p1. Okay, now if I drew out an orbital diagram to demonstrate this, right? If I looked at beryllium here, if I drew out an orbital diagram, we have helium, and then we have 2s2, right? And if I take a look at boron here, let's use a different color. We have helium out here. We have 2s2, and we also have the p subshell. So this valence electron, which fills one of the p subshells, is really far away from the nucleus, right? So when you move to a different subshell within the shell, you're actually further away from the nucleus. And because you're further away from the nucleus, the separation distance increases, right, between the nucleus. As a result, the effective nuclear charge will decrease, and if the effective nuclear charge decreases, the force of attraction will decrease. So it's kind of counterintuitive to going to the right of the period, right? We said that going to the right of the period, right, the force of attraction increases because there's a higher effective nuclear charge. In all these 3 cases, right, these 3 cases here, right, as we go to the right of the period, right, so as we go to the right of the period here, the nuclear charge increases, the effective nuclear charge will tend to increase, and as a result the force of attraction increases, and all of these things will be affected by the force of attraction. Well, now we're saying that as we're going to the right of the period, the separation distance increases because there is a new subshell that gets created. Okay, and furthermore, because you get a new subshell that's created, you also have filled subshells being existing, right? So this is an example of a filled subshell. So we've shown a filled subshell here, like this is an example of a filled subshell, this is an example of a filled subshell. The more filled subshells and core electron shells you have, the more shielding you get, right? So subshells will also create shielding, and filled subshells or spin-paired subshells will also cause increased shielding with core electron shells. And this is what we call subshell shielding. Right, so we have more subshell shielding, right? So collectively, our shielding actually improves, it increases. Because shielding increases, separation distance increases, and as a result, the effective nuclear charge decreases, and the force of attraction will decrease. Okay, so this is actually going to bring an important concept down that we need to actually look at subshells as well, right? So because of this notion, atomic radius in that case actually increases sometimes to the right of the period. And if atomic radius increases, then there's going to cause, and as atomic radius increases, what's going to happen here is the ionization energy actually decreases, and the electronegativity decreases, and the electron affinity decreases. So look what happens to all of these guys. So as atomic radius increases, the ionization energy decreases, the electronegativity decreases, and the electron affinity decreases to the right of a period. So this is where some of the exceptions might occur. Exceptions may occur to periodic trends due to subshell shielding. Okay, so it's a very important concept to understand. And also remember, we are looking at these trends, they're just predictive measures, right? We're predicting certain cases, but it's not always going to be right. It's just important to understand how this stuff is working out, but there will be exceptions, and it's because we don't have the full picture, and one of the reasons we don't have the full picture is because we didn't consider subshell shielding. So we'll take a look at this notion, we'll look at some exceptions and some examples, but for the most part, the periodic trends will work for about 85% of the cases. Right? The other 15%, you have to look at other things, specifically the quantum mechanical model.